Last class we have done in detail about the indicators. The last topic in this indicator chapter is acid-base titration curves. We have discussed 4 different curves of acid-base titrations: strong acid, strong base, weak acid, strong base, strong acid, weak base, and weak acid, weak base titration curves we have discussed. Today, let us discuss the pH calculation of this titration. First, let us take the titration of a strong acid versus a strong base. Strong acid versus a strong base. Example, for this strong acid, strong base, let us take titration of HCl versus NaOH. So, what is the change in pH at the end point that we have to calculate here? Here, let us take 25 cc of HCl solution in a beaker and 25 cc of 0.1 normal HCl solution in a beaker, and in the burette 0.1 normal NaOH. Let us, for example, we have taken. So, both of them are strong acid versus strong base. Now, in the beginning, when you take 25 cc of 0.1 normal HCl, the pH is very low. The pH is very low, less than 2. pH is very low here. Now, when you go on adding sodium hydroxide, pH goes on increasing. It increases like this. It increases like this. At the end point, what happens? At the end point, there is sudden rise of pH. There is sudden rise of pH. Actually, at the end point, when there is complete neutralization, HCl reacts with NaOH to form NaCl and H2O. NaCl and H2O. Here this strong acid and strong base. So before neutralization, even if there is 1 drop of HCl is there, definitely pH is very low. And after neutralization, even 1 drop of NaOH if you add, pH suddenly rises and it will become basic. So pH, how to calculate a pH? What is the pH of neutral solution? For that, you can take water. Water undergoes hydrolysis to form H plus and OH minus. It is a very weak ionization is there. It weakly ionized to form H plus and OH minus. So from this equation, from this dissociation of water, we can calculate the pH of a neutral solution. So let us say the equilibrium constant is represented by K. By applying the law of mass action, K we can write it as K is equal to concentration of H plus ion into concentration of OH minus ion divided by concentration of H2O. Now, because these two are constants, we can represent this as Kw. This Kw is nothing but the ionic product of water. Kw is equal to H plus ion concentration into OH minus ion concentration. So, by knowing H plus ion concentration or OH minus ion concentration, we can easily explain the pH of a solution. Now, actually at 25 degree centigrade, this ionization, 25 degree centigrade, this ionization takes place to form the concentration of H plus as 10 to the power of minus 7 and concentration of H plus OH minus is 10 to the power of minus 7. Actually 1 in 10 to the power of 7 molecules undergoes ionization to form H plus and OH minus. Therefore, at 25 degree centigrade, this H plus ion concentration is 10 to the power of minus 7 and also OH minus concentration is also 10 to the power of minus 7. If you multiply these two, this becomes 10 to the power of minus 14. This is the ionic product of water at 25 degree centigrade. At 25 degree centigrade, the ionic product of water, Kw is equal to 10 to the power of minus 4. Therefore, what is the concentration of H plus ion and what is the concentration of OH minus ion? We know that concentration of H plus ion is 10 to the power of minus 7. 10 to the power of minus 7 is a very small quantity. Therefore, to express that in terms of integers, we take negative logarithm of this. So, negative logarithm of Kw is called pKw. pKw, negative logarithm of ionic product of water pKw. So, is equal to negative logarithm of H plus ion concentration, that is pH, and negative logarithm of OH minus ion concentration, that is pOH. So if you take negative logarithm of 10 to the power of minus 14 into minus 10 to the power of log 10 is 1, therefore its value becomes 14. Therefore ionic product of water can also be expressed as pKW. pKW is equal to 14. pH and pOH is nothing but pH 7 and pOH 7. Therefore at neutral point, at the point of neutralization, pH is 7 and also pOH is 7. pH plus pOH is 14. If you know the value of pH, you can calculate the value of pOH, or if you know the value of pOH, you can calculate the value of pH. Suppose if pH value is 6, pOH is equal to 14 minus 6, that is 8. pOH is 8. So when pH is 6, pOH is 8. Therefore pH 7 or pOH 7 is the neutral point. So here, before neutralization, even if small amount of acid is there, pH is very low. Therefore at the neutral point, the pH which has a small amount of HCl, pH is 4. After the addition of one drop of sodium hydroxide, pH suddenly jumps from 4 to 9. That is because one drop of NaOH means one drop of 0.1 normal NaOH means 1 liter of the solution contains 10 to the power of minus 3 liters into 10 to the power of suppose if one drop, if you take 1 ml has 100 drops, that can be written as 10 to the power of minus 2. Therefore it becomes 10 to the power of minus 5. pOH is 5. pOH is 5. Therefore pH is 9. So therefore suddenly pH changes from 4 to 10. And we discussed about the indicator range. Different ranges are there. Methyl red, for example, the indicator range is 3.2 to 4.5. Methyl orange 4.5 to 6.5, and parathymal blue 6.5 to 8.5. Phenolphthalein indicator 8 to 10. This is the pH range of various indicators. So here in this rise in pH at the end point, which rises from 4 to 10, you can use indicators here. Any indicator can be used. For example, methyl orange, which has the range 4.5 to 6.5, which comes here, that indicates the end point of the titration. Another indicator is phenolphthalein indicator, which has pH range but between 8 to 10. So here that change is also there between 8 to 10. Therefore you can use either methyl orange or phenolphthalein indicator as we have explained earlier. Therefore the pH calculation, pH at the end point changes from 4 to 6, and that's why you can use any indicator in this range as I have shown here. You can use methyl orange or phenolphthalein indicator in case of strong acid, strong base titration. But in case of strong base weak acid titration, the nature of the curve is different. For example, weak acid strong base versus strong base. Example, acetic acid versus NaOH solution. So how this titration will be, how the end point, how the titration pH titration curve will be for this titration, let us see. In this case, acetic acid reacts with the sodium hydroxide. In the beginning, acetic acid, it has pH less than 7. When you go on adding sodium hydroxide, because this is a weak acid, immediate neutralization takes place and suddenly the pH changes. If you see the curve of this titration, it is like this. In the beginning pH is 2, it slowly increases and when it comes to the neutral point, there is sudden rise in the pH between 8 and 10. There is no rise in the pH less than 7 because acid is weak. So only this range, 2 units between 8 and 10, therefore only you have to use phenolphthalein indicator in this titration. In this titration, you can use phenolphthalein indicator. Why there is rise only in this range between 8 to 10, that we can see by the calculation, by the reaction. Acetic acid reacts with NaOH during the titration to form sodium acetate and water. But the sodium acetate and water, of course. So the sodium acetate which is formed here, that undergoes hydrolysis because it is the salt of a weak acid and strong base. It undergoes hydrolysis to form acetic acid and sodium hydroxide. Acetic acid and sodium hydroxide. Here the product it is a weak acid, but the base is strong, therefore pH rises. POH rises here. pH is, the sodium hydroxide is a strong base, it is a weak acid, therefore pH goes towards above 8 because of strong sodium hydroxide, weak acetic acid. Since this is weak acetic acid, there is no rise in the pH in the acidic medium, only change in the pH in the basic medium. And also we can calculate the pH of this reaction by using equation. Now this is hydrolysis, KH, hydrolysis constant. Here acetic acid undergoes hydrolysis. This acetic acid which is formed here, it undergoes ionization to form CH3COO minus plus H. This is a reversible reaction. Therefore, you can apply law of mass action to calculate the equilibrium constant of this. This equilibrium constant is represented by Ka. Ka is equal to concentration of the products by concentration of the reactant. Concentration of the product is nothing but CH3CO minus concentration into H plus concentration divided by concentration of acetic acid. Now you can rearrange this equation. You will get acetic acid concentration into Ka concentration into acetic acid concentration is equal to acetate concentration into H plus concentration. Therefore, you have here H plus term. So this H plus term gives you the pH of this reaction. Therefore, H plus concentration is equal to Ka into CH3COOH concentration divided by CH3COO minus concentration. We know that to convert this H plus concentration into pH, you have to take negative logarithm. Negative logarithm of H plus to the base 10 is nothing but pH. That is equal to negative logarithm of Ka is pKa. So, and this becomes minus log of acid by this is nothing but the salt. Acid by salt. If you make into plus, it becomes log of salt concentration by acid concentration. Thus, pH can be determined for this reaction. In case of weak acid, we can calculate the pH of the titration. So, the pH range in this titration is between 8 and 10. Therefore, only you have to use phenolphthalein indicator in case of a weak acid, strong base titration. So another type of titration is strong acid, weak base titration. In case of strong acid, weak base titration, strong acid, weak base. Strong acid versus weak base. Strong acid versus weak base. Example, HCl versus ammonium hydroxide. HCl versus ammonium hydroxide. So this is the volume of ammonium hydroxide added. Volume of the ammonium hydroxide added. Now let us see how the pH changes at the end point. Now you take 25 cc of HCl solution in the conical flask, add ammonium hydroxide from the burette. Since acid is a strong acid, pH is less than 7, and when you add ammonium hydroxide, there is no sudden jump in the pH at the end point because it is a weak base. There is no sudden end point here, but acid is very strong. Therefore, the pH is around less than 2 in the beginning. So at the end point, when 25 cc of 0.1 normal ammonium hydroxide is added, what happens? The pH of the solution changes like this, and there is a rise of pH in this range between 4 and 6. There is a rise in pH. So in case of ammonium hydroxide titration, the pH rise will be there between 4 and 6. Therefore, you have to use methyl arrange only here. In case of weak base titrations with strong acid, you have this range between 4 and 6. Therefore, methyl arrange should be used here, and you can calculate even the pH at this end point. Actually, the reaction here is HCl reacts with ammonium hydroxide. HCl reacts with ammonium hydroxide to form ammonium chloride and water. So this ammonium chloride is the salt of a weak base and strong acid. Here this ammonium ion undergoes hydrolysis. To form ammonium hydroxide and H+. So this H+ combines with Cl-, again it forms a strong acid, whereas ammonium hydroxide is a weak base. Therefore, even at the end point, even at the neutralization point, HCl is produced there. And ammonium hydroxide is a weak base formed there. Therefore, the pH is in the acidic region itself. So therefore, the change only in the acidic region, that is pH between 4 and 6 in case of weak base titration. Therefore, you have to use methyl arrange indicator only, and you can calculate the pOH of this solution. It is a reversible reaction. You apply the law of mass action, K equilibrium constant, K is equal to, here, it has been given here, K is equal to, apply law of mass action, equilibrium constant K is equal to concentration of the products over concentration of the reactants. NH4 plus concentration and H2O concentration. H2O concentration is almost constant, and this is the hydrolysis of a base. It is represented by Kb. Therefore, we can calculate pH of this titration. pH calculation, you can take negative logarithm to the base 10 both the sides, and change this towards this side and convert that into pH. Therefore, pH can be calculated as shown earlier. So pH of this solution neutralization can be calculated, and it will be between 4 and 6. That is about strong acid versus strong base titration. And pH is determined, and pOH can also be determined by considering the dissociation of water. Therefore, pKw is also considered here. Sorry, this is pKw is also taken into consideration. So pOH and pH can be calculated. So that is about the titration of a strong base or a strong acid versus weak base. This is the shape of the curve. Now last type of titration is titration of a weak acid versus weak base. Weak acid, acetic acid for example, versus weak base, ammonium hydroxide. This is weak acid, example, weak acid versus weak base. Weak base. So in this titration what happens? So since both of them are weak, neutralization is not sharp because there is no complete ionization of either acetic acid or ammonium hydroxide. Sudden change in the pH will not be there. Therefore, if you see the curve of this titration, there is slow change in the pH. So there is no sudden rise in the pH, any pH. Therefore, you cannot use any indicator. This is methyl orange indicator range. This is phenol indicator range. Therefore, indicators of no use here. You cannot use any indicator in this type of titration because there is no sudden jump in the pH at the end point. Therefore, indicators cannot be used here, and this type of titrations cannot be carried out using this titration method. So that is about pH calculation and pH curves of acid base indicators. So that is about indicators chapters. Next, we shall pass on to the next topic, that is liquid mixtures. Liquid mixtures. Mixing of two or more liquids is nothing but liquid mixture. In this liquid mixtures, if you mix only two liquids, that is called a binary liquid mixtures. Binary liquid mixtures. Binary liquid. You mix two liquids, any two liquids. For example, you mix water and alcohol, you mix triethylamine and water, mix nicotine and water, benzene and toluene, many liquids, oil and water, you mix two liquids. That type of mixture is called binary liquid mixtures. These binary liquid mixtures, all binary liquid mixtures are not identical. They show different behavior. They show different solubility. So depending upon that, these binary liquid mixtures are further classified as partially miscible liquid pairs. Partially miscible liquid pairs. That means the miscibility is partial at a given temperature and at given composition. It's not the miscibility is not complete. It is complete at special conditions. At high temperature, at various concentration, it may be highly miscible, but at ordinary temperature, at ordinary conditions, it is partially miscible liquid pairs. Examples of this type, very important examples are water and triethylamine. Water and triethylamine. Another example is water and nicotine. Another example is water and phenol. Very important example. Water and phenol. Many pairs you can give examples. So these pairs are at a given temperature, ordinary condition, at say 25 degrees centigrade, normal conditions. They are not miscible completely. They miscible partially. For example, if you take water and triethylamine, if you mix these two, little water is soluble in triethylamine. Similarly, little triethylamine is soluble in water. Little. Therefore, and there is a separation of two layers. You can see two different layers because slightly soluble. They are slightly soluble within themselves. Therefore, these type of partially miscible liquid pairs is a separate class. In this type, what happens, if you take this mixture, any mixture, and if you go on heating at a particular temperature, These partially miscible liquid pairs are completely miscible above that temperature. That temperature at which a partially miscible liquid pair is completely miscible is called critical solution temperature. Critical solution temperature. Critical solution temperature is the temperature above which a partially miscible liquid pair is completely miscible. So therefore, we have to study this critical solution temperature in detail. Another type of binary liquid mixture is completely immiscible liquid pairs. Completely immiscible. Completely immiscible. So in these completely immiscible pairs, there is no solubility at all, not even 1%, no solubility at all. Completely they are insoluble. For example, you can take toluene and water, toluene and water, oil and water, mercury and water. These are completely insoluble. Third type of this binary liquid mixture is completely miscible liquid pairs. Completely miscible liquid pair. In this completely miscible liquid pairs, there is no any hindrance at all. At any proportion, at any temperature, they are completely soluble. Very good, very important example is ethyl alcohol and water. Ethyl alcohol and water, benzene and toluene. These liquids, irrespective of the temperature, irrespective of the composition, they are completely miscible at all conditions. Those are called completely miscible liquid pairs. Therefore, these binary liquids can be classified into three classes: partially miscible liquid pairs, completely miscible liquid pairs, and completely immiscible liquid pairs, and completely miscible liquid pairs. Now, let us study in detail this partially miscible liquid pairs. In this partially miscible liquid pairs, we have water and triethylamine, water and nicotine system, water and phenol system. Let us study this in detail one by one. Partially miscible liquid pairs. Partially miscible liquid pairs. First, I will take up, instead of nicotine, I will take phenol water system. Phenol water system. What is this phenol water system? What happens here? Now, if you mix equal volumes of phenol and water, a small amount of phenol is soluble in water. About 4% of phenol is soluble in water. A small amount of water is soluble in phenol. Now, if you take in the container, in a beaker, this mixture, what happens? Two layers, you will see. Two layers. One is water layer, another one is phenol layer. Phenol layer and water layer. So, these two layers are separated by a separation. But phenol contains little water. Water also contains little phenol. But what happens? There is separation. Because there is only small amount of solubility is there, separation will be there. So, in this phenol water system, you take a mixture of phenol and water and you heat it. If you go on eating this mixture, they become a single layer, a uniform layer, a solution. Completely one is soluble in the other, complete solution. That is possible at this temperature. This is the temperature. This temperature. So this temperature is 66 degrees centigrade. At 66 degrees centigrade and above, phenol and water is soluble in any proportion. You take any proportion of the mixture. Above this temperature, it is completely soluble. But below this temperature, what happens? At a particular composition, this is composition of phenol, and water. You take water, go on increasing the percentage of phenol, mole fraction, percentage of phenol. Okay, percentage of phenol, you go on increasing. What happens? When the phenol is less, completely soluble. When the phenol is less, completely soluble. When the amount of phenol increases, solubility decreases. Two layers are separated here. Two layers are separated. Because phenol, more amount of phenol is not soluble in water, less than 66 degrees centigrade. So this is the region. This is the region where there is separation. Above this, when phenol amount increases, water amount decreases, there also there is complete solubility, completely soluble. So this is the region, solubility region where these two water and phenol is completely soluble. So this temperature above which water and phenol is soluble in any proportion, this is the critical solution temperature of phenol water system. Critical solution temperature of phenol water system is 66 degree centigrade. That is the speciality of this partially soluble liquid mix. That is one example. Another example is triethylamine water system. In this triethylamine water system, the condition is different. Actually, when you mix water and triethylamine, solubility will be more at lower temperature, at 18 degree. At 18 degree centigrade, below the temperature, completely soluble. Therefore, these two are partially miscible liquids. They are highly soluble below 18 degree centigrade, and within this composition, when the temperature is above 18 degree, it is partially miscible. When the amount of triethylamine is less than this proportion, it is completely miscible. Or when water is less and triethylamine is more, that is because the attraction, intermolecular attraction between these two molecules will be different at various concentrations and temperature, whereas below this 18 degree centigrade, the molecules, they attract each other in the normal condition, therefore they are soluble with each other. Therefore, this 18 degree is the critical solution temperature. Here the critical solution temperature is above 66 degree, above standard condition. This is called upper CST. This is upper CST, upper critical solution temperature. This is lower CST. This has lower CST, lower than the atmospheric temperature. So this partially miscible liquid pair phenol water system has got upper critical solution temperature, whereas triethylamine water system has got lower critical solution temperature, less than atmospheric temperature. So that is the speciality. There is one more example, special type, that is which has both upper and lower CST. Upper and lower CST. Actually, it's not lower than atmospheric temperature. There are two critical solution temperature. One such example is nicotine water system. In this nicotine water system, this is water. This is nicotine percentage. This is the miscibility temperature. What happens at this temperature? It is 68 degree. This is 208 degree. This 68 degree. See, below 68 degree it is soluble in all proportions. Above 208 degree, both of them are soluble in all proportions. But within this region, they are partially soluble. Even when the water is more, nicotine is less soluble, or when nicotine is more, water is less soluble. But in this region, it is partially soluble. So there are two critical solution temperatures. One is upper critical solution temperature 208, lower critical solution is 68. Lower critical solution means it is not lower than atmospheric temperature. There are two critical solution temperatures, 68 degree. Therefore, this is the speciality of this partially miscible liquid pairs, and this partially miscible liquid pairs, above the temperature it is soluble, that is called critical solution temperature. There is one more effect in this critical solution temperature. That is, when an impurity is added to these mixtures, the critical solution temperature is varied. Critical solution temperature is varied. For example, in case of phenol water system, if you add little impurity, if you add a little sodium chloride, critical solution temperature increases. Now, to this phenol water system, you add a solute or impurity, critical solution temperature is more than 66 degree centigrade. For example, you can determine the critical solution temperature of various percentage of the impurity. You measure the solubility temperature, and you add different percentage of the impurity, or percentage of the solute if you add. If you go on adding the percentage of the solute to this a known mixture of phenol and water, what happens? Critical solution solubility temperature, so solubility temperature or miscibility temperature, both of them are the same. Miscibility temperature goes on increasing. Therefore, as the percentage increases, miscibility temperature increases. You can see that. So therefore, by drawing a graph, we can determine the purity of the solvents, or also you can determine the amount of the solute dissolved in the solution. So miscibility temperature versus percentage of solute, you can determine the percentage of solute dissolved, or you can determine the composition of phenol and water system, that is about partially miscible liquid pairs. Now take the second type of binary mixture, that is completely miscible liquid pairs. Completely miscible liquid pair. So in this completely miscible liquid pair, examples are ethyl alcohol water, ethyl alcohol plus water, benzene and toluene, and so on. So many examples are there. These are completely miscible irrespective of the temperature and composition. Completely miscible. So ethyl alcohol and water, they are completely miscible. Benzene and toluene are completely, whatever may be the proportion, they are completely miscible. Here, what happens here? The vapor pressure of the pure component, either ethyl alcohol or water, the sum of the vapor pressure of these two will be constant at all composition. When the vapor pressure of a component A is equal to its vapor pressure in its standard condition and its composition, that is mole fraction of A. If the vapor pressure of a component A in the mixture, vapor pressure of alcohol or water above that liquid layer, this vapor pressure of a component A, if it is equal to its vapor pressure in the pure state and its composition in the mixture, if this is equal to this is called an ideal solution, and the law is called Raoult's law. Raoult's law says that vapor pressure of a component in the mixture is equal to vapor pressure in its pure state multiplied by its mole fraction in the mixture. If it obeys this at any concentration, at any temperature, that is called an ideal solution. An ideal solution is one which obeys Raoult's law at all conditions of composition as well as temperature. Raoult's law states that the vapor pressure of a component in the mixture is the product of the vapor pressure in the pure state multiplied by its mole fraction in the mixture. So ideal solution is one which obeys Raoult's law. But majority of the completely miscible liquids are not ideal. Majority of them are non-ideal. but they approach ideality at some special conditions. So therefore, so let us study some examples which deviate from Raoult's law, which deviate from ideality, and which obeys Raoult's law. So if you draw the graph of vapor pressure versus composition of these completely miscible liquid pairs, as the vapor pressure increases, the percentage composition also increases. Percentage composition also increases. For example, if you take benzene and toluene, benzene has got benzene and toluene vapor pressure, just not vapor pressure, visibility temperature. Sorry, not vapor pressure only. For toluene, benzene has got lower vapor pressure when compared to toluene. Toluene has got higher vapor pressure. So if you go on changing the composition, 100% benzene has got this vapor pressure. 100% toluene has got this vapor pressure. When you go on increasing the composition, vapor pressure goes on increasing and you will get a straight line. This is ideality, ideal behavior. But if you take the vapor pressure composition curve of alcohol and water, what happens? Water has got lower vapor pressure and alcohol has got higher vapor pressure. As the amount of alcohol increases, vapor pressure increases. So therefore, the graph will be deviated like this. At a particular composition, it is above maximum vapor pressure of the mixture. This is the particular composition where 95.5% alcohol and 4.5% water. 95% alcohol and 4.5% water, isn't it so? So this deviation is above the normal value. This is called positive deviation from Raoult's law. So this mixture, alcohol and water, they deviate from Raoult's law. This deviation is above normal, therefore positive deviation from Raoult's law. Similarly, if you take the mixture of sulfuric acid and water, what happened? There is negative deviation from Raoult's. There is negative deviation. This is the shape of curves obtained. So this is for benzene and toluene. This is for ethyl alcohol and water. And this is for sulfuric acid and water. So in case of benzene and toluene, they show ideal behavior, ideality. There is a straight line in the vapor pressure composition curve. Whereas in case of ethyl alcohol water, there is deviation at a particular composition. I have mentioned here the composition. In this composition, there is deviation. Deviation is above normal. That's why it is called positive deviation. Positive deviation from Raoult's law. Similarly, if you take sulfuric acid and water, there is negative deviation from Raoult's. Therefore, all completely miscible liquid pairs are not ideal. All of them do not obey Raoult's law. Some of them deviate from Raoult's law. The deviation may be positive or negative. So deviation from ideal behavior, positive deviation from ideal behavior and negative deviation from ideal behavior. So therefore, we shall discuss some more concepts of these completely miscible liquid pairs in the next video.